anyone has any idea what was wrong with this? Oh,
I
Bahari?
have one question.
Yes, please.
S0 is the point that we are here is now, and infinity is the future, or I think
so
time is missing here.
So this integration, S is a flux, right? So integration is all the flux. So infinitely bright flux to zero flux, very faint one. So this integration is just from here to here, all of the area calculating. So these are bright stars, these are faint stars, and we want to integrate all the brightness of stars.
Okay, but our universe is limited, have time in it, and one
very good point.
That is near to Big Bang never had the chance to we can see their light. And,
yes, you're getting there. Yes, very good point.
And I think it's the reason that we cannot see the whole stars and their fluxes now. Maybe 1 million years later, their light becomes reach the Earth. Not yet.
Yes, that's a very, very good point. Anyone want to have comments? Angel?
I think I had a similar idea.
Yes.
I had the idea that this.
You had the Angel's paradox.
No.
Or a similar idea with Bahari. Okay.
Similar idea to hers. I said that like these formulas, these equations don't take into account like the Big Bang or the expansion of the universe. And so I was thinking like if we take into account the expansion, by default we are going to have less number density of stars in any given area of the sky. And so that also has to do with like the lack of the time factor in the equation.
Very good point. Yes. Fidan?
Yeah, I also had a thought about the assumption we did in the beginning. We said that the density is constant, so we have like a homogeneous universe, and also we don't say anything about the radius being bounded. So we have essentially like infinitely many stars. And I think that's quite a strong assumption.
Yes, very good point. Anyone else have any opinion? Okay, see?
I was thinking about this, that we not considering the absorption or by dust.
Another very good point. Yes.
And in regards to, exactly, and with adding to Angel's point, yes, because of the expansion of the universe, say the light from a distant star, from all the stars in our path, the light from the star, because of the expansion, would get redshifted, and
and
so say if it was emitting in a particular wavelength, it would move on to a different wavelength, not exactly the visible light.
True.
Because of that, could be another reason why we are not seeing the
Yeah,
light
exactly. Yes.
So
Very good point. So basically, all of you are correct. So the fact that universe, its night sky is dark, means there are not enough stars. In other words, the age of the universe is not infinite. So as you guys mentioned, I assume that I started from the assumption that there are infinite number of stars. I said the billions of stars. So whatever direction you look, you end up with a star. In a situation, I should have shown this simulation, but how do I click this? can I show this? Did I share the screen? So I started with this kind of assumption, right? If I look at, if there are billions of stars, so if you look at any direction, you end up with a star, so the night sky should be bright. But our night sky is dark, so that means there aren't infinite number of stars. So in reality, it will be like this. So I also talk about, show you an example of a forest. If there are enough trees, yes, you end up looking at the tree, but then our night sky is dark means there are not enough trees. So you look at some direction, there are no stars. So that's why you see the night sky is dark. And then that means the size of the universe is finite. And then that's because age of the universe is finite.
Also, the age of the stars. Stars are dying after their duration of their age.
That is also true. Yes, yes, that is also correct. Yeah. So you know, from the, so that means, so we just look at the night sky, right? Oh, then you should know, oh, our universe is not infinite, right? That's what we learn from the night sky. That's cosmology. Okay, but then, you know, I like this example because from a very simple observation that night sky is dark, there are, you know, some important things we learn from. So I like this example, you know. Then, you know, I can imagine nowadays we have, you know, many large telescopes and we have a lot of data. So there may be a lot more to learn about our universe. And then, okay, so you guys, okay. Then another additional question is, okay, maybe I should, I should, okay. Okay, you guys did a very good job, but there are some smart people. It's amazing. So this Olbers paradox was proposed by Olbers in 1843, right? But in 1610, Johannes Kepler already raised the issue and suggesting that the universe might be finite. Isn't it amazing? This is 200 years before Olbers asked the question. Johannes Kepler already knew the answer. And then furthermore, sorry, it's 1823 Olbers. Yeah, Olbers, you know, it's actually people ask questions before Olbers. And also in 1848, do you know the novelist Edgar Allan Poe? He's a famous novelist. He's sort of called that he started a detective novel, and he also wrote a novel called The Black Cat. It's a very scary novel. Like I don't know what cat, black cat, like it says meow, and there's a dead body of this guy killed or something like that. So it's so scary. I don't want to read it again. But I recommend you to read. It's a very good novel. So anyway, so this Edgar Allan Poe is a novelist, but in 1848, in his essay, already know that the universe might not be old enough for light all stars to have reached us. This was early intuitive recognition of the importance of the universe is finite, of the universe's finite age. So in his essay, that he already knew that, the universe's age is not infinite. It's amazing. Some people are smart. So Olbers paradox is not a paradox. It's already, there's an explanation, right? I sometimes see on an archive that, a paper saying, I solved the Olbers paradox. But that's not okay. It's already not solved. So, okay. Okay. And there's an additional question that I ask. What's the difference? So I ask a question. I did the discussion 1 and 2, right? So what's the difference between 1 and 2? So in 1, I said that the night sky should be as bright as the sun's surface. In example 2, I said the sky should be infinitely bright. What's the difference? Does anyone know? Yes, Jeremy?
In the first scenario, just consider one layer. In the second one, you integrate the whole of the bound universe.
Yes, that's correct. So the first one, I stopped, right? When I hit the star, it stopped, right? So that's why the sky brightness is the brightness of one star. But in second one, I'm integrating all through, right? So there may be a star behind a star, right? Star and a star, 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 right? So if you integrate everything, it becomes infinite. So that's the difference between 1 and 2. Okay, any question? Can I move on to the next topic? I still have time, right? This class is until 5:10, right? Is that right? Okay. Okay, then next I want to talk about the basic of cosmology. It may be boring to you, but then I will explain to you as easy as possible. Okay? This is a foundation. This is like XY of the cosmology, so we need to know about it to further discuss. So this is something called metrics we need to talk about. So invariant, okay, we need to talk about. So when we discuss the motion of a difference in coordinates, so if it's an xy plane, we talk about delta x and delta y, right? And then say if this point moves from here to here, what's the difference? Distance. Then it's x squared, y squared, and a square root, right? But then in the universe, it's 3-dimensional, right? So x, y, z, right? So we need invariance x, y, and then delta z. That's okay, right? Because it's 3-dimensional, right? And then in addition to this, we need to add time. Time, universe is changing as a function of time, right? So in special relativity, we need this term, c delta t. So invariance becomes c delta t minus x minus y minus delta z squared. Okay? So now x, y, z 3-dimensional plus time. Okay? So that's invariance when we talk about universe. And then when we talk about expansion of the universe, it's more convenient to use spherical coordinates because universe expansion is in radial direction. It doesn't, expand only x direction or only y direction. It expands in every direction, so in radial direction. So it's much more convenient to have spherical coordinates, something like this. So the r is a radial direction and a theta and phi. So this radial direction and the angle, theta and phi, instead of x, y, z. Okay? So we introduce spherical coordinates. So we write this thing in spherical coordinates matrix. So now this is delta t time, right? And r radial direction, and then theta and then phi. This is just a spherical coordinate. Okay? Nothing complicated. Okay? Then universe is expanding, we know. So we need to describe we want to describe expanding universe, bigger or smaller, right? That's what we want to discuss. Then we introduce the simplest way. We want to do it as simple as possible. And then we introduce something called scale factor, this RT. And then put it on top of this coordinate, positional coordinate. And then this R, scale factor, is going to describe how many times the universe is larger or smaller. So if R becomes 2, then universe is 2 times larger. If it gets a 4, it's 4 times larger. That's more convenient than changing individual one separately. Because we have this R theta phi, right? And if we choose to increase, okay, universe is 2 times larger, okay, let's make this 2 times larger, this 2 times larger, this 2 times larger. That's inconvenient, right? So we separate that factor of expansion of the universe here. That's why it's called scale factor. That's easier to describe, okay? And then this is something called okay. And then, okay. Now, then we need a curvature. This is assuming that the curvature of the universe is flat. Geometry of the universe is flat. But it's not necessarily flat. Universe of geometry may be closed or open, something like this. Okay, this is assuming flat universe where parallel light keeps parallel. But the universe may be something like this. So the parallel light, if you're on the surface of a sphere, the parallel light is going to close eventually, right? If you're surface of something like this, then your parallel light is going to separate into different direction, right? Something like this, right? These may be the case of the universe. So we need to put it in here as a curvature. So K is here. So K is describing this curvature of the universe. And then we put it K here. Okay. And this is the so-called Friedmann-Robertson-Walker metric. This is the simplest coordinate system to describe the universe, including expansion and then curvature. By the way, this is still assuming homogeneous and isotropic, meaning that you look at this direction and you look at direction and universe is more or less similar in large scale, which is true observationally. And homogeneous means this is also true, you know, from this side of the universe and then this side of the universe, it's essentially the same, which is also observationally true. We will come back to this observational evidence later in the semester. But assuming, you know, this, for example, if the curvature is different from this way and this way, one equation cannot describe it, right? So we're just assuming this one equation can describe the universe. If the expansion of the universe is different this way and this way, then one scale factor cannot describe it, right? But we are assuming it's one factor, which is probably okay. Okay. So okay. So then we came up with this. This metric is famous Friedmann-Robertson-Walker metric. This is the simplest metric to describe expanding universe with curvature. Okay. Okay. Well, there are various. This is just a coordinate system, right? So you can take different coordinates. For example, black hole. If you want to describe black hole, you can take a more convenient metric for black hole. But for expanding universe, this is the simplest, and we like simple one, right? Okay. Don't worry about it. Curvature is almost zero. We know that curvature is almost zero from CMB observations, cosmic microwave background observations. So this term is almost you can ignore. And we assume, you know, the universe is isotropic. So these terms is most cases you can drop it. So you just need this. So that's simple in actual calculations. Okay. I just wanted to know where this came from. Okay. Now, we want to derive the Friedmann equation. Friedmann equation is an equation to describe expansion of the universe. So basically, you know Einstein equations, right? It's common sense, right? Einstein equation is a common sense. You put this Friedman-Robertson-Walker metric into Einstein equation, this into Einstein equation, and then you get these two, these Friedman equation. This is derivative version, differential version, and this is integrated version. So just simply, okay, we are not going to do it. This is a lengthy calculation to put in Einstein equation. But so we are not going to do it in a class. But then if you're interested, you can just look at the textbook. They owe you, it's maybe 1 page of derivation. This. But that, you can just check the textbook. But what's important is how these two are very important equations. So I wanted to understand where did this came from, and that's combining Einstein equation and then Friedman-Robertson-Walker metric. Okay. Einstein equation is just the curvature and energy, right? So if there's a curvature, if there's a gravity, that's bend the space. If the massive object such as black hole, then geometry around it is bended. So the mass, gravity equals curvature. That's Einstein equation, right? If you're interested, that's, I think, you need to, if you take a general relativity course, like, they will teach you that. But we just take it as a fact, okay, in this course, and use it. And then so you put it in a different way, and then you get this Friedman equation. Okay, then what's the meaning of this Friedman equation? Okay. Okay, so the meaning of the Friedman equation is this is a scale factor, right? Scale factor. So the size of the universe, and then you take a time derivative. So this is a sort of expansion speed of the universe. This is unitless, but this expansion speed of the universe. So expansion of universe is decided by these 3 terms, okay? And then this is basically gravity, okay? You see density of matter, density of radiation, which is very small. So, and then you see the gravitational constant there, right? So this term is gravity, okay? Mostly from dark matter, as we see it later in the semester. And then this term, as you can see, K, this is curvature. So curvature of the universe. What kind of geometry is the universe? And then this term, as you can see, lambda here, is from the dark energy. So the meaning of this Friedman equation is expansion of the universe, expansion speed of the universe, is decided by these 3. So curvature, I said it's almost 0, right? So this is very small effect, okay? And so it's just a tug of war between gravity and then dark energy, expansion, dark energy. So if the dark energy is large, this expansion speed is going to be large, right? It's positive. So universe is going to keep expanding faster and faster, faster. If gravity is large, this is going to be opposite. It's going to shrink, 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 or slow down, slow down, slow down. So that's what this Friedman equation is, the meaning of this Friedman equation. So it's up to us to decide the future of the universe. So we can measure this dark energy, how much is there, dark matter, how much is there, and then we can decide, we will know the future expansion speed of the universe. as we can see this later in the semester, we will see there's a fine-tuning problem. It's a very interesting problem. In a universe that we live at the moment, these two are in the same order. So it's a balance, it's similar. So that's the reason why we can exist. And then that's one of the unsolved puzzle of this cosmology. If this is dark matter is too much, everything becomes black hole. The sun and earth and then we, human, cannot exist in the black hole. If this is too large, everything's gonna expand and then, bye-bye, Darian, and we never see you. You're far away. Not just people, our molecules and then, atoms will be far away. So if this is too large, we cannot exist. If this is too large, we cannot exist. But it seems like our universe is fine-tuned so that we can exist. That's one of the puzzles of the universe. It's called fine-tuning problem. Okay, and then the second line is this is a differential form of the Friedman equation. So these two are called Friedman equations. If you differentiate this, and then you get this. And then depending on occasion, we can use either different forms of these Friedman equations. Okay. Do I have time? Any questions so far? Is it okay? Okay. Do we have a time dilution? A time to talk about time dilution. I'm not so sure. Well, next topic is time dilution, but I don't think I can finish it in 15 minutes. So maybe we stop it here. Maybe we can just relax for the first class. Okay. So, yeah, let's stop here. Then next week we have just a regular class, right?
And two presentations.
Okay. So, Jeremy and then Junhao are going to present, right? Yeah, okay. Thank you very much. And then please prepare for presentation. Okay. Okay. Then let's stop here. If you have questions, you can just come here or TAs and then ask questions. If you don't have any questions, see you next week. Okay. And then please make sure sign up for your presentations.